let's talk about a lot of different topics. So we're going to look at motion. We're going to look at one-dimensional motion, kinematics, scalar versus vector, distance versus displacement, how we mathematically add displacement vectors, and how we graphically add displacement vectors. So this video has lots of different topics. Okay, so let's get started. So motion. How do we know if an object is moving? Real simple. An object is in motion, so a moving object, there's going to be a change in position. Okay, so for something to be moving or for something to be in motion, its position has to change. Okay, so if you look at my head or my pencil and you look at the ceiling tiles behind me, if my head moves relative to those ceiling tiles, then it's considered in motion. Okay, so for an object to be moving, it has to have, or there has to be a change in position. Okay, so one-dimensional motion is it's the simplest type of motion. So with one dimension, like an object will move forward and backwards, but it won't move right or left. Or it'll move right and left, but it won't move forward and backwards. So it's motion in a single dimension. Like think it's motion in the X dimension, or it's motion in the Y dimension, but it's not motion in both dimensions. Okay? So that's one-dimensional motion. I always think about a commuter train. It goes back and forth, but not side to side. Or an elevator. It'll go up and down, right? It's moving in the Y dimension, up and down, but not side to side. So it's moving in a single dimension, okay? I want to look at this term kinematics, okay? When you go to college, you're not going to take a PE. It's not called a PE. It's called a kinesiology. So if you think about ology, like prefixes, so ology is the study of, and then kine. So biology is the study of bio, which is life. Kinesiology is the study of motion. So when we think of this kine, we should think motion. And then the matics part is the mathematical description of motion. Okay, so that's where we get kinematics, this term. So we're going to be looking at one-dimensional kinematics. And again, if an object is in motion, its position changes. So frame of reference is really important. It's important to have a frame of reference so that we can measure these changes in position relative to that frame of reference. So a coordinate plane is a great frame of reference. And normally 0 is like our frame, and then we can measure changes based on that 0 position. So that's really good. So, and then I want to look at very quickly the difference between scalar quantities and vector quantities. I think I spelled that right, yeah. So a scalar quantity would be like time or mass, or we're going to learn distance is a scalar quantity. It refers to magnitude only. And you may be thinking, okay, what's magnitude? When you think magnitude, think size. How much, how big, okay? So, for example, when we talk about mass, the mass of that object is 100 grams. That 100 refers to the size or the amount or the magnitude, okay? Vector quantities like we're going to learn velocity and displacement and acceleration. Vector quantities describe both magnitude and direction. So think back to Despicable Me, Vector, right? He's a villain committing crimes in both magnitude and direction. Oh, yeah. Okay. So think magnitude, how big, and then also in what direction. So when we look at distance and displacement, distance is a scalar quantity, whereas displacement is a vector quantity. Okay. So distance is how much, how big. It's the length between any 2 points. Okay. Displacement, however, is the length and the direction. And displacement's a little bit more specific in the sense that it's the change in position measured from the starting point, which is usually our 0 on our frame of reference. Okay. So the primary difference, distance here tells you nothing about the direction of travel, whereas displacement tells you precisely how far and in what direction from the initial position. How far from the initial position and in what direction relative to that initial position, which most often, not always, the initial position is 0. Think of distance as the total length and think of displacement as the net length, accounting for direction. Okay. So displacement, there are actually 2 equations. The displacement, you can think of this as the change in position. It is the final position, xf, minus the initial position, xi. If we're talking about the x dimension. If we're talking about the y dimension, you'll see delta y equals the final y or vertical position minus the initial y or initial vertical position. Okay. There's another equation for displacement, and this really has to do with vector addition and the mathematical way to add vectors. So the total displacement and this little arrow over delta x, that just means that it's a vector quantity because you're going to learn that we represent vectors with arrows, okay? And that is just adding the individual displacements. Vector addition, okay? All right, so let's look at a problem, and I think that it'll make a lot of sense. So the first problem, let's say we have a runner, and he is starting at point P, so that's our initial position, which I'm just going to say is 0, okay? And let's say that our runner runs all the way to point S and then comes back to point R. Okay, so we're starting at point P, we're running to point S, and then coming back to point R. So R here would be our final position. All right, so first thing I want to determine is I want to determine the total distance. And here's my equation. Now remember, distance is a scalar quantity, so we don't have to worry about direction. Distance is just the total length of travel, okay? And all we're going to do here is just add up our distances. So from point P to point S, that is a total distance of 15 kilometers. That's right. And then from S to R, that's a total distance of 7 kilometers. So our total distance here is 22 kilometers, and that represents the magnitude, how big, the size of the distance, okay? So that's distance. That's pretty easy. Now I want to calculate displacement, and we talked about how there's actually two ways to calculate displacement. So the first one, I'm just going to use like the whole adding vectors mathematically. So delta x total is equal to delta x1 plus delta x2. So we're just going to add the individual displacements together to find the total displacement. But remember, displacement is a vector quantity, so direction is important. And normally when we talk about direction, this is important. Okay, normally to the right is positive, to the left is negative, up is positive, and down is negative. Think of an XY coordinate system, okay? Also, you can think of like north, south, east, west. So normally east is positive, west is negative, north is positive, and south is negative, okay? So what I'm going to do here, notice my first displacement is going to be 15 kilometers, okay? But that is to the right, so we're going to say positive to represent that direction. And then my second displacement is 7 kilometers, but it's to the left, so we're going to put a negative to represent that direction, okay? And so here, 15 minus 7, that would be 8 kilometers. That would be the magnitude of the displacement. And then we can put positive to represent the direction. Or you could put 8 kilometers to the right. Okay? So that's one way to determine the displacement. Another way would be you use this equation x final minus x initial. Okay? So in this case, the final position is R, which would be the 8-kilometer position, and the initial position is 0, which is point P here. And so we can see that our displacement is 8 kilometers. That's the magnitude, and then positive, that positive represents the direction. Okay, makes sense. So now I want to talk about vectors a little bit more. So we represent vectors with arrows. The length of the arrow represents the magnitude, whereas the direction that the arrow points in obviously represents the direction. Okay? When we add vectors, we add them tip to tail. So if we have multiple vectors that we're adding together, we add the tip of one vector to the tail of the next vector. So that looks like the tip of this vector is to the tail of the next vector. So we add vectors tip to tail, and then we have the resultant vector, which is also known as the vector sum. Okay, so that's the sum of adding these vectors together. Normally, the vector sum will go from the tail of the first vector to the tip, I should say tip, of the last vector. So in this case, the resultant vector would start here at the tail of the first vector and go to the tip of the last vector, the second vector. So I want to show you how to add vectors graphically versus mathematically, okay? And you can see we kind of have a little vector diagram going on right here. So our first vector was 15 kilometers long. to the right, and then we added the second vector, tip to tail, and then our resultant vector would go from the tail of the first to the tip of the last, and that resultant vector is 8 kilometers long and pointing to the right, which that's where we get the whole positive direction. So graphically, all right, so here's the graphical method of adding vectors. There's some steps that we're going to take. Step 1, determine a scale. And that kind of depends on what you're given in the problem. Determine a scale. Did we freeze up here? Oh, there we go. Okay. So what we're going to do down here, well, and I'll show you later, but we're going to do 1 kilometer equals 1 centimeter. That's a scale. Again, your scale can vary depending on what you've got going on in the problem. 2, we're going to draw a vector diagram. And the vectors have to be drawn to scale, right? Using a ruler. Using a ruler. Okay, you're going to draw resultant vector. And then you are going to measure the length of the resultant vector to determine the magnitude of the resultant vector. So let me show you how this works. Maybe. There we go. I'm going to move this down a little bit. So in the above problem up here, we were adding this positive 15 kilometers to this negative 7 kilometers. So my scale here, I've actually determined my scale. 1 kilometer equals 1 centimeter, okay? So we're going to draw our vector diagram to scale using a ruler. Here's my ruler. So we're going to have a vector that is 15 centimeters long. And my ruler's a little crooked. So 15 centimeters long, which represents the 15 kilometers to the right. And then we're going to add these vectors tip to tail. So my other vector is going to be 7 kilometers to the left. And you could put those on top of each other, but then it's kind of really hard to see, especially if you're doing this with pencil. So I just put it a little bit below. Okay, so there's my vector diagram. I'm adding tip to tail. And then my resultant vector is going to start at the tail of the first and go to the tip of the last. So this is my resultant vector right here. And then, if I'm doing my steps, draw the resultant vector, done. Measure the length of the resultant vector. You can see that the resultant vector is 8 centimeters long, which translates to 8 kilometers. That's the magnitude. And then you can also tell that my resultant vector points to the right. So my direction here is either to the right or positive. All right.